this is the periodic table, and in the far left column, these are the noble gases. Helium, neon, argon, krypton, xenon, radon. The name noble reminds you that they're kind of snooty and they don't react with anything else. They don't interact much with anything else. So it's very unusual and difficult to create compounds of these elements. It's unusual to see them. It does happen once in a while under crazy conditions, but they're extreme conditions. Immediately to the left of the noble gases, you have these elements which are called the halogens, and you have other nonmetals. So this group here called the other nonmetals, carbon, nitrogen, oxygen, all these nonmetals, the halogens and the other nonmetals, these elements will tend to gain electrons to get the nearest noble gas electronic configuration. This is all really fancy. I mean, I'm using all these big words, but it's really a simple concept, and you'll be able to do this like all day, and it's not a problem at all. I'll prove it to you. So if someone asks me, hey, will fluorine, like if fluorine is forming an ion, will it be a positive or negative ion, and what will the charge be? I would look at the periodic table. I'd find fluorine. It's in this column that's one to the left of the noble gases. It's a nonmetal. It's to the left of the noble gases, like on this side of the periodic table versus way over here in the metal zone over here. So what I would say is, hey, by the way, this is also called the P block. So it's in this P block area. So I'd say, look, it's going to gain electrons because it's a lot easier for it to gain electrons to have a stable electronic configuration like neon than it is to lose all these electrons, to lose 1, 2, 3, 4, 5, 6, 7 electrons to have the electronic configuration of helium. So this is going to gain 1 electron. Since electrons have a -1 charge, it's going to have, as an ion, a -1 charge. So fluorine starts with 9 electrons. By gaining 1, it has the same number of electrons as neon, 10. But fluorine has 9 protons in the nucleus. So it's going to have 1 more electron than it has protons. It's going to have a -1 charge. So if I look at this like second column with oxygen, sulfur, and selenium, each of these elements will gain 2 electrons to have a noble gas configuration. So oxygen can gain 2 electrons to have the same noble gas configuration as neon. By gaining 2 electrons, that means it's going to have a -1, -2 charge. So it's going to have an overall -2 charge by gaining 1, then another electron. Same with sulfur, same with selenium. Nitrogen, it's 3 electrons shy of having the noble gas configuration of neon. So it's going to gain 1, 2, 3 electrons. It'll have a -3 charge. Carbon, it's 1, 2, 3, 4 spaces away from neon. It's 4 electrons shy of having the noble gas configuration of neon. So as an ion, a carbide ion would end up having a -4 charge. Does that make sense to everybody? These are the nonmetals. They gain electrons, and you can tell from their position in the periodic table how many electrons they need to gain to have the nearest noble gas configuration. For the next thing. Okay, so on the other hand, there are elements in the transition metals and in this S block that will lose electrons to form ions. They'll actually form positive ions by losing negatively charged electrons. And these positive ions of these elements are called cations. So, for example, sodium, by losing just 1 electron, would have the same electronic configuration as neon, right? Going from 11 electrons to 10. So just by losing 1 electron, it goes to a stable electronic configuration. So that's what it'll tend to do if it's in an ionic compound, is it'll actually lose an electron. Calcium, for example, has 20 electrons, but by losing just 2, it has the same electronic configuration as argon. So it'll actually lose 2 electrons. It starts off as a neutral element with 20 protons and 20 electrons, By losing 2 electrons, it'll end up having 18 electrons and 20 protons. And that means it has 2 more protons than electrons, so it has a +2 charge when it does this.
So it's always just trying to get rid of 2.
Yeah. These metals in particular aren't very tricky. If you see this in a compound, it's almost always going to be +2 for anything over here in this column, +1 for anything over in this column. Hydrogen is a little trickier, but these other things, pretty much all the time, you're looking at a +1 ion and a +2 ion for these. These things, if you make these metals, if you make these elements on Earth, you have to protect them from air and water because they get oxidized. We live on Earth. There's a lot of air and water. So you make these things, you put them under like mineral oil or some kind of looks like petroleum oil type goo, and hopefully that keeps the water away from it long enough so that you can store this on like a cabinet shelf for a while. And even then, over time, like they start building up oxides and stuff. So what I'm talking about here is that if you have on Earth these sort of oxidizing conditions, you have these nonmetals present around a lot, they'll react with metals and they'll form ionic compounds. So in general, if you see a compound of some sort of metal and a nonmetal, you're looking at a ionic compound. This is going to be a compound where the metal has lost electrons, is positively charged, and the nonmetal has gained electrons, is negatively charged. So that's an ionic compound. This is different from when there's sharing of electrons. If you see compounds that have multiple nonmetals, these are molecular compounds. They have sharing of electrons. Not give and take, but sharing of electrons. So they're fundamentally different. They form molecules, they have actual bonds. Sodium chloride or table salt, that's Na+ and Cl-. It's an ionic compound. And really what this mostly is it's a sodium with a plus charge, a chlorine with a minus charge, and these ions are attracted to each other because positive and negative charges attract. Not because they're bound at the hip, not because they're sharing electrons, but because of that electrostatic attraction. Okay. So in ALEX, you're given these different molecules, cesium fluoride, HBr, and nitrogen trifluoride. So we can figure out whether or not these are ionic or molecular compounds. Okay, so if I just look at the periodic table and figure out where these elements are, I would find that cesium is on the left side. It is a metal. So here's cesium. It's a metal. It's going to lose an electron. It's going to be positively charged. And if I look at fluorine or fluoride ion, kind of giving it away already by calling it fluoride, I end up having this be a nonmetal, right? It's over here on the right-hand side of the periodic table. So I can just mark that down, right? Metal, nonmetal. So this is going to be ionic. Metal, nonmetal, it's going to be an ionic compound. HBr, I don't like this question. I think it's kind of tricky. I think in real life there is a little bit of a covalent bond there, but if I had to use Chem 101 rules, I would have to say that it's the same situation. You have an element on the left-hand side, the H, and the bromine is on the right-hand side, so it's going to be a nonmetal. And I would have to say, if I had to characterize this, I would say that it is ionic for now. So if you go on in chemistry, you'll find that this is an acid and that really there is a bond there, but it's kind of weak. So it's kind of like getting borderline. Finally, NF3, these are both nonmetals. If I go look at the periodic table, I see that N is here. It's on the right-hand side. Fluorine's here. It's on the right-hand side. They're both classified as nonmetals or halogens, so they're both nonmetals. They're both accepting electrons or sharing electrons in this case. So that's a molecular bond. So understanding where things are in the periodic table really helps you figure out what kind of bonding is involved in a compound. It's also important for naming and being able to convert an element to its ion and being able to figure out what a formula is from the name of a compound.